So it's the last presentation of the day. I hope you still have some energy. So I'm going to show 3 examples because my time is limited. Basically, you can see Passivhaus is working worldwide. This is the definition of the Passivhaus. You can see that there's no mention of climate and it's based on physical laws. But what is important is you shouldn't take a German Passivhaus and put it like this in Portugal because it won't work. You need to adapt your project to the local climate. And so we have been doing a study about cost-efficient and energy-efficient buildings worldwide, and we came up with this map. Basically, each color corresponds to a set of parameters. For instance, the dark blue, where we see Germany, would be around 300 millimeters of insulation for walls and triple glazing, while for Portugal, it would be a warm climate in yellow. This would be more around between 10 and 15 centimeters of insulation for walls and double glazing. And these are guidelines that are displayed in PHPP. It's just to start draft your project. Of course, after you need to adjust it, because each project is different. And you need to pay special attention at the waterfront and microclimates. So I'm going to start with a project in Mexico. It's a warm climate zone, and it's the first Passivhaus without heat recovery, because the temperatures are so mild in Mexico that we don't need it. Basically, it's a house that was built quickly on the top of another one. It was built with temporary material. So when we made it to the Passivhaus standard, we replaced many materials and we added some insulation to get to those U values. We changed single glazing through double low E glazing. And we have an exhaust ventilation and cross-natural ventilation. So the air is coming somewhere around here and it's extracted somewhere at the bottom over there. And with these measures, we managed to get a lower heating demand and heating load. And also, we don't need active cooling, whereas before people were suffering from very hot temperatures in summer and spring and discomfort in winter. Now I'm going to present you 2 projects that are part of the Seed Pass project. It's a European project that is providing training material that is adapted to the traditional construction methods and climates of Croatia, Italy, and Greece. So this is the example for Italy. It's a warm temperate climate, so a bit harsher than in most regions of Portugal. You can see that it's a modern building, but it's not very compact. That's partly why we will need very good U values, as you can see here. Regarding the windows, they have been using triple low E glazing. To be honest, we usually recommend windows to be installed aligned with the insulation layer. So here I wonder if we would have done it, installed the window in the insulation layer, it wouldn't have been enough to have double glazing. But it's up to everyone to use the solution they would like, as long as they respect the final criteria in PHPP. So they're using a ventilation with a high efficiency and a heat pump and radiant floor heating. And in this project, they have both a heating and cooling demand, but they are quite low. And now this is a retrofit in Athens. So it's a really interesting project because we have the simulation through PHPP and some monitoring results. So this is a building, it's now finished, this one, but before it was a building of the 60s. And its envelope was mostly with concrete pillars and perforated bricks in between. And what the owner did, he added a layer of 15 centimeters of insulation around this building. So you can see the U values before. He also added some insulation in the roof and on the slab. Now they are much better. And he also reduced the thermal bridges. So he wrapped the parapet and the balcony with insulation to limit those thermal bridges. This is not the ideal solution for a new building, but for an existing building, you have to deal with what is already there. Regarding the windows, before he had some wooden windows with double sash. He changed them with single sash windows so he can enjoy more solar gains. And before he had single glazing, now he's having triple glazing. And you can see here he's installing it in the insulation layer to limit the installation thermal bridge, which is what we usually recommend. And another thing, he was also augmenting the glazing surface on the south in the kitchen, and he found out with PHPP that this had a very great impact on the energy balance of his building. Regarding ventilation now, so before Stefan had, if I remember well, a boiler and radiators and a fireplace for the heating. And now he has put all this away and replaced it with the ventilation unit that he's also using to distribute heat in his building. He's also using a mini split, mostly for cooling, but it's also useful in case he would need a backup for heating. And he also has a subsoil heat exchanger to preheat or pre-cool the air before it arrives in the building. And these are the results. Now you can see that if he wanted to heat his building to 20 degrees in winter, he would have had a demand of around 300 kilowatt-hour per square meter in a year, while now he has something around 11, which is quite very good improvement. Cooling is also lower, and with those values he could have actually certified his building to the Passivhaus standard, but since he retrofitted it, he wanted to certify it with the NFIT standard, and he added recently some PV panels to reach the NFIT Plus class. Now, really interesting slides, because here you will see that you can reach the Passivhaus standard with different alternatives. So if you remember well, we can reach the Passivhaus standard either by having a heating cooling demand lower than 15 kilowatt-hour per square meter in a year, or a heating and cooling load smaller than 10 watt per square meter. He could have reached this criteria with 10 centimeters of external insulation and double glazing, but he wanted to get the certification with this criteria because if your heating cooling load is lower than 10 watt per square meter in a year, you can use the ventilation system usually to distribute this heating, which he wanted in his case. So he could have reached this criteria with 20 centimeters of external insulation and double-glazed windows with a high G value. But unfortunately, those windows were not available on the Greek market. So he needed to try another option, 15 centimeters of external insulation and triple glazing, and that's how he reached the Passivhaus standard. And at the same time, could do away with the traditional boiler and just use the ventilation system to distribute heating. So here are the results of the first monitoring. As you can see, because I forgot to mention that there are two floors. The top floor is for the family, and the ground floor is with an office. And you can see here that even in the office, the air quality is always very good. The CO2 concentration is never exceeding the stricter limit of 10 parts per million. It's around 900 at most. And it's important, as we have been talking a bit earlier, to give the user this data because then they can see that it's really working. Now these are data about the heating demand and the cooling demand in the first month of monitoring, and you can see that the deviations are really small between what we have simulated with PHPP and what has been measured so far. You always need to keep in mind that maybe here there's 6 kilowatt-hour per square meter and per square meter of difference, but what is 6 kilowatt-hour in comparison to the 300s? And also we are simulating a building with climate data that is taking an average of the past 30 years. The more we can get, the more data we can get. But it could be that in this year, February was a bit colder than usually or warmer. It's always depending on the year. And now coming to cost. So in PHPP, I've mentioned this morning that there is a sheet where you can compare two variants according to cost. In this sheet, you can enter the price, the energy price of your country, and how much did your investment cost. So this project retrofit cost 50,000 euros, almost in total, which is a normal cost for Greece for a retrofit, and represents 400 euros per square meter. And now you can see in red the annual cost for heating. In blue, the new annual cost since the building is retrofitted, and in green, this annual cost for heating and taking the loan as well into account. And you can see that if Stefan wanted comfort, that's to say 20 degrees, from the first year, it's actually better to go for an energy-efficient retrofit because it's cheaper to pay back the loan instead of having your building uninsulated with single glazing and consuming so much energy. And I think that was it. So to sum up, passive house is working in different climate zones, and you can reach comfort and energy efficiency with different building variants, as we've just seen with the Greek example. What's really important is that you try out different options in PHPP and that you select the one that is the most coherent with your needs and also with your context, be it climatic or economical. Thank you.